değerli araştırmacılar tarafından lisansüstü öğrencilerimize ve siz değerli akademisyenlerimize sunulmuş, verimli bilimsel sohbetler yapılmış ve grad workshoplar ile disiplinler arası çok değerli akademik tartışmalar gerçekleştirilmiştir. Fen Bilimleri Enstitüsü'nün markalaşan Grad Talks'ları için başta rektörümüz Tamer hocamız olmak üzere rektör yardımcımız Zeynep Işık hocamıza, doçent doktor Murat Hüdaverdi ve profesör doktor Nezir Aydın hocalarımıza destek veren tüm ekibe çok teşekkür ederiz. Grad Talks'larla yakalanan bilimsel sohbet platformlarını aynı heyecanla üniversitemiz Sosyal Bilimler ve Temiz Enerji Teknolojileri enstitüleriyle işbirliği içerisinde zenginleştirerek sürdürmek amacıyla bugün Grad Talks serisinin 38. semineri ile karşınızdayız. Grad Talks seminer serisinin 38. konuğu Doktor Sheffield'e katılımı için çok teşekkür ederek hoş geldiniz diyorum. Hello Dr. Sheffield, thank you very much for accepting our invitation. Welcome to the 38th Grad Talks seminar. Şimdi de sizi selamlamak üzere sözü Sosyal Bilimler Enstitüsü Müdürü Murat Donduran hocamıza bırakıyorum.
Thank you, Belkıs hocam. First of all, I thank to John Sheffield for giving us his valuable time for this presentation. I hope these online meetings and in the future we will plan some other workshops and some other conferences give to the participants very valuable insight and perspective about several topics. And of course, thank all of the contributors for Grad Talks, past and future issues on behalf of my institute, which is Social Science Institute, and of course, on behalf of Yıldız Technical University. Welcome to this meeting by John William Sheffield. Thank you again. Okay.
Temiz Enerji Teknolojisi.
Herkese merhabalar, değerli hocalarım, sevgili katılımcılar. Tabii ki biz de Temiz Enerji Teknolojileri Enstitüsü olarak özellikle temiz enerji odaklı, işte sizlerin ufuklarınızı açacak konuşmacılarımızı buraya davet etmeye ve ağırlamaya çalışıyoruz. I would like to take Professor Sheffield to accept our invitation and valuable talk. Now, Nader Javani is going to moderate this Grad Talks meetings. Now, your turn, Nadir Hocam. Thank you again for all the participants.
Hello, everyone, and thank you for joining this event. I really appreciate Professor Sheffield to accept our invitation despite of the tough schedule I know he had this week. On behalf of Yıldız Technical University, I really thank Professor Sheffield. So, Professor Sheffield is a well-known professor in the globe, and so it's not difficult to find so many introduction passage about Professor. So briefly, I will talk about the some main parts. Professor Sheffield is a president of International Association for Hydrogen Energy. Upon the retirement of Professor Necat Gaziroğlu, Dr. Sheffield was elected as the president of International Association for Hydrogen Energy, having previously served as the executive vice president. He was appointed a member of the advisory board of the Hydrogen GRP, a joint research platform, and in April 2022, he was selected for 2022 Outstanding Leadership in Globalization Award from Purdue University. At the same time, Professor Sheffield joined Purdue University in 2015 as a professor of engineering technology. Saying this and knowing that these were just a part of his brilliant biography, I'm going to give the floor to Professor Sheffield, and we're interested to have your valuable time, Professor.
I will share my screen now. So before I really start the talk, I would like to comment that it was 50 years ago today that as a young graduate student, I was introduced to the late Professor Öszösek, who was a classmate of Necdet Veziroglu when 6 Turkish students from ITÜ went to England for their studies. And it was through Professor Öszösek's work that I had the opportunity to meet and work with Necdet. And to this day, I still enjoy conversations and talking with him. So let's look at this graduate talks for hydrogen energy developments and outlook. And I'll start with this part that we can think of the role of hydrogen in emission mitigation, a carbon neutral value chain. So we can think of that as the power to X, or P2X, as some people say. So we can start out with renewable power. We might envision that as wind, solar, hydro, tide, geothermal, biomass, waste energy, and even some people consider the nuclear. The hydrogen that can be then produced, and we often will think of that in terms of a clean hydrogen or a green hydrogen production. Further in the carbon neutral value chain, we have the storage and transportation of the hydrogen, or the hydrogen derivatives by ship, trains, trucks, and pipelines. And at that point, we might inject in with our green hydrogen, blue hydrogen, where we have carbon capture and storage, and also the hydrogen derivatives such as ammonia. And it's this ammonia that I will pay some attention to today, because that will be one of the technologies that's mature enough that it's at the inflection point this year. And then we go into the green hydrogen utilization and the derivatives such as green ammonia. So we have, of course, the blending of hydrogen with natural gas enrichment to industry and power generation. And just last week on Thursday, in UK, the hydrogen infrastructure legislation was passed, and it has £100 billion infrastructure development funds that will do. So we see some major changes and major steps moving forward in this role of mitigation. But let's start with what is green hydrogen. And I think this is a very important one that we need to answer and remember. And so green hydrogen is hydrogen produced by splitting water from electrolysis using excess renewable electricity. And I want to talk about that concept of the excess renewable electricity. And this is where it distinguishes between the nuclear and the renewable energy sources, where we have the intermittence of the renewables. So for many, including the oil and gas sector, large industries from steel to fertilizer, green hydrogen is regarded as the best bet for harmonizing the intermittence of that renewable energy sources while decarbonizing the important energy-intensive industry, chemical, and transportation sectors. So here again, we can revisit the clean hydrogen value chain and green. They have the green hydrogen infrastructure of the power generation from renewable and the electrolysis and the electric grid. So when we have the renewable, what we desire, as facilitated by the legislation from UK last week, is to overbuild the renewable energy. That is from solar, wind, offshore and onshore, and in their cases in UK, tidal and currents. So in this case, when we have the excess renewable, then we produce the green hydrogen. Potentially, we can blend that with the blue carbon, so we have a clean hydrogen value chain. And the next, we can go to the gas turbine power plants. GE, for example, this year has 11 gas turbines ranging from 34 megawatts that can be commissioned in 11 days and packaged on trailers to 600 megawatt units. In the gas engines here in Lafayette, Indiana, Caterpillar makes a genset that is a 1.25 megawatt backup power or standby power systems that can be used in hospitals and other important in uses, commercial uses. In natural gas pipelines, this is a major part, particularly for areas where they begin to improve that infrastructure. For example, in the Netherlands, the desire is to achieve 100% hydrogen capabilities of their natural gas pipeline distributions. In refineries and petrochemical applications. And so in this, we'll see some applications here that I will focus on, and we'll explain why those are occurring. But even in UK, the legislation that passed last week, there's residential. So the residential boilers will have to be replaced and new infrastructure with hydrogen being the energy source. Now, let's turn our attention to a report that was released the 22nd of September this year from the International Energy Agency. And this shows a map of the systems. And what we find out here is that the map of these announced low emission hydrogen production projects, that if we look at the green squares, we have the operational electrolyzer projects, and most of those are in Europe. But if we go to the under construction blue electrolyzer projects, we see a lot in China, and the capacities are noted in the column there. So that gives us some reference, if you will, to why we want to look at this one, and that is in China. In the ongoing projects, the capacity growth from 2020 to 25 is quite significant. And so we see on the left the installed capacities in gigawatts, and the installed capacity and size in gigawatts. And what's important is that 2025, we see the top of that bar chart in red. That is the gigawatt size electrolyzer. And this is crucial to the development of the hydrogen energy infrastructure worldwide. With that, another figure in that report from the Global Hydrogen Review from IEA is the technology readiness levels of the production of low-emission hydrogen and the synfuels such as the green ammonia. And the top is in blue, and the ones that show dots in there are the infrastructure, in particular for the ammonia tankers and trucks of all carriers and storage tanks for all carriers. And it's at that ones that we will focus on the first country that we'd like to identify. And the light blue is the market uptake. In the mid-range and the demonstration, yellow prototypes, and the base here is the small prototypes. So what we like to do is then look at Singapore. And I was just there, returned on Saturday from being in Singapore. Singapore has a national hydrogen strategy. The global developments of hydrogen are at an inflection point for Singapore, with increased investments from countries and companies globally to develop new technologies and establish supply chains for clean hydrogen. And Singapore believes that the clean hydrogen has the potential to be a major decarbonizing pathway to support Singapore's accelerated transition towards net zero by 2050. Now, Singapore is a new city-state. It was established in 1965. And so their economic development is really a model for us to look at. And so standing at this inflection point in a global hydrogen development. So let's look at some examples of hydrogen as a green solution for Singapore. And this shows the example in the two end uses that are critical for the economy of Singapore is shipping and aviation. And so it begins to give me a little bit of a potential analogy to Istanbul. Shipping, of course, the Bosphorus, and the new airport with aviation and the role that Turkish Airlines has. This gives us the Singapore gives us a good illustration for some analogies. In the value chain, we went through the power to X, but once we have that to intermittent renewables, then it's to hydrogen to power, that is to generate the electricity. So in Singapore, there's a lot of investment in solar PV, and it's operating 24 hours a day city, and so they need that nighttime electric power. There's another part of this is that Singapore plans to build the capacity to import, handle, and utilize green ammonia as the hydrogen carrier or direct as a fuel for power generation. Ammonia supply chain development will support marine bunkering needs. Now, Singapore just received their first green ammonia shipment 2 weeks ago. So they're in this process. In addition, Singapore is developing over a multi-phase in the next 15 years, a megaport, potentially the biggest port in the world. The port of Singapore is currently the world's busiest container transshipment port, with ships arrival tonnage exceeding 2.8 billion gross tonnage in 2021. Singapore is also the largest bunkering hub, supplying close to 50 billion tons of marine bunker fuels to vessel fuels using the international shipping routes in 2021. As a major global maritime hub, Singapore can play a very important role in decarbonizing, especially through the transition to low-carbon fuels. To this end, they unveiled their Maritime Singapore Decarbonization Blueprint in 2022 and have already decommissioning some of their old ports and shipping container and moving towards a fully automated system. Sorry. So the international maritime sector is undergoing a green transition that will span the next few decades. And what Singapore has seen is it's already begun. That is, engine manufacturers have made progress in developing engines that can directly burn the green hydrogen derivatives, such as green ammonia, and large global shipping lines have already ordered new fleet builds to run on these engines. These developments are reflected in the latest industry projections for maritime fuel transition, which estimates ammonia and clean hydrogen onboard fuel technologies can be available well before the end of this decade. So normally we think of 2030 as inflection point, but in the maritime, the inflection point is in fact this year. Singapore plans to focus on decarbonizing the port operations and transition to the domestic harbor craft, in this case, fully electric propulsion and net zero fuels. And by 2050, the container handling operations will be electrified, supplemented by low carbon energy sources such as hydrogen. They envisioned that all the harbor craft will operate full electric propulsion or net zero fuels to achieve net zero emissions by 2050. Their harbor, the Megaport Harbor, complete renovation or development and building is by 2040. So there's a lot of risk here, financial risk. There's also the challenge in terms of ammonia. It will need a larger land space that Singapore doesn't have, and they also need some type of safety protection, which in this case is a double water shower or curtain and protection in case of accidents. So not only there's a safety for the green hydrogen, but also for the green ammonia is paramount in their development and their research. The airport in Singapore is perhaps the one of the most advanced airports. As a frequent international traveler, I've always impressed because they use full facial recognition for all entry and also boarding of the planes. So it's quite an impressive operation. And at the recent 41st International Civil Aviation Organization Assembly, held in September and October last year, they adopted a long-term aspiration for a goal for international aviation to achieve net zero emissions by 2050. And my colleagues here at Purdue University, the Aerospace Engineering, which is now the largest aerospace engineering program in the United States, that they envision that by 2085, that commercial aviation will be 100% hydrogen. So sustainability is this key priority for Singapore's aviation sector as well in the coming years, as it revives their air travel and rebuilds the Singapore Air Hub. At the same time, Singapore will also play its part in contributing to decarbonization of global aviation. So aviation and shipping are essential in this case, and Singapore is a good example. Now, let's change our mindset a little bit and think of it from the point of view of traditional oil and gas. And so the full hydrogen value chain has a variety of sources of value and challenges at each stage. So much like we think of in the oil and gas, we have upstream, midstream, and downstream. In the value chain, we can think of what the values are and what is included. And this graph illustrates. And if we then change and look at what the source of the values are, for each of these upstream, midstream, and downstream, we see these listed here. And if we continue along that same path and look now at what are those challenges for each of the value streams, and we see a variety. So it's important to do this. And what I was mentioning just before we started was that I'll be in Vienna in 2 weeks for the 7th technical meeting of OPEC and OPEC plus countries, and they're looking at hydrogen and how we mitigate it. And the particular focus is on Asia, and particularly for countries of Japan, China, South Korea, and then how that integrates in the global. And so let's look at that Hydrogen Council. The Hydrogen Council was established, and members are the chief executive officers of major corporations and now a variety of other interests. And the report issued just a couple of weeks ago shows the hydrogen decarbonized energy system in today's system and in the future systems. And we see the dramatic change, or the coupling, the sector coupling between the oil and gas and electric infrastructure. That's an important thing to remember in our race to zero, so to speak, to 2050. So very quickly, here are some of the hydrogen decarbonizing systems. So we bring this system benefits in addition to decarbonizing to hard-to-abate sectors. As an example, we can take resource-rich regions that need prioritizing connecting renewable sources to demand centers via hydrogen pipelines. We can take resource-poor regions that focus on maximizing the value of their limited resources, can use curtailed power to make hydrogen. And island power systems need to pay extra attention to the flexibility which electrolyzers and hydrogen turbines can provide. The island powers can also be thought of not necessarily a physical island, but remote power systems. And so this last August, I was in South America and Peru and looking at a brand new copper mine developed by Anglo American. And that mine is 100% renewable power from wind. All of the material handling equipment, the mining trucks that carry 400 metric tons, the payload, the shovels, and all are electric drive. And the mining is 100% digital and automation ready. So we're seeing in some of these island systems, that is remote power systems, where the decarbonization. And it turns out the mining trucks alone represent 2% of the total emissions, carbon dioxide emissions in the world. So by decarbonizing those thought of to be hard, remote locations, hydrogen has a major role. Electrolyzers is a key, and it's the response to the market prices to alleviate these supply-demand crunches in the system, and those levels of the intermittent. And as we transition to developing renewable, one of the biggest game changers is going to be offshore wind. So hydrogen provides the resilience against the most challenging parts of the year when renewable loads is low and energy demand is high. Now, finally, we think of the network infrastructure in the sense of market design rules, critical enablers, hydrogen and the CO2 pipelines. For that, allowing electrolyzers to respond to prices to ensure lower overall cost. And now let's look at a recent report from September this year from the Asian Infrastructure Investment Bank. So I want to share with you just touch base with a couple of recent reports in the last couple of months from financial institutions. So the Asian Infrastructure Investment Bank study reviewed the global conditions for clean hydrogen production use cases to identify possible engagements. And the economic modeling identified the likely least cost hydrogen production locations and hydrogen use cases in countries with significant potential based on both short, medium, and long-term technical and economic viability. As an example, Saudi Arabia with the NEOM project is looking at a massive investment where the target price by 2030 is $1 per kilogram. In the U.S. terminology, if we want to explain to somebody, we can say that's $1 per gallon of gasoline equivalent. So those are really cost competitive situations. Of course, from financing, what we have to do is not just the technology, but we have to change our mindset. And that mindset from the financial banking, instead of looking at the capital cost to develop a new project, our mindset has to be from total cost of ownership. So not only the CapEx, but also the OpEx, the operating expenditures. Operating expenditures include system integration. So as a graduate student, this is an important thing for us to start thinking about. Not only do we have to develop the technology, but we also have to operate it and maintain it. So the total cost of ownership follows what our predictions have indicated. Another report is from the Asian Development Bank Institute, and this was just out last month. And the takeaway here in this hydrogen and decarbonizing strategies for Asia and the Pacific is that green hydrogen produced by renewable energies could be the game changer solution for both energy security and ambitious climate targets. So again, this is from the perspective of Asia. Another report from the Asia Development Bank, it was just released in July this year, is looking at the strategy for 2030, that inflection point of the energy sector directional guide. So this gives us some guidelines to promote the low carbon energy sources, including hydrogen and supporting initiatives that drive the global transition towards clean energy. So it's mobilizing investment. And this was July. And on October 26th, the UK, for example, passed the £100 billion infrastructure investment legislation. And what's interesting in UK that's not seen in Asia at this point is the cost for the initial cost, sort of the CapEx component, instead of being burdened to the end use, the residential user, is being covered by the gas supplier, the industry sector. So this is better because the investment cost really should be covered, if you will, by that industrial sector. And I think this is important from a societal point of view, and it's sort of thinking of is addressing the question of social justice when we look at these new transformations that we're seeing worldwide. So with that, I want to give us plenty of time. I hoped for the 30-minute point to say thank you, Teşekkürler, and to be able to answer questions. So I will before we stop sharing, I'll put my email up there. So if you want to take a note, it's the Sheffy, John Sheffield, J. Sheffy at Purdue. And with that, I will stop sharing and hope to be able to answer as many questions or take referrals and answer those. So thank you.
Thank you. Thank you very much, Professor Sheffield, for your eye-opening speech and changing our mindset about the future of hydrogen technology. So we have room for a couple of questions, if there's any from the audiences online. Any question? So I will start with one question myself, if you let, saying that the, let's say, hydrogen storage problem is an issue that we are facing nowadays. And considering, let's say, the ammonia and green methanol, which one you think is a better solution in terms of capex, resiliency, security, and other stuff to have, let's say, a better solution for the sustainable future?
Okay, so it's an excellent question, and probably I'd like to answer that from the current perspective, and that is these large sectors where the gigawatt electrolyzer is viable, and that tends to be in the replacement of conventional technologies. And so the port of Rotterdam in the Netherlands is the example. It's the largest port in Europe. It's a fully automated port already. It already has the tonnage gas operations of a refinery there, analogous to Singapore. They have 3 refineries. In Singapore, Shell is trying to avoid stranded financial assets of the fossil fuel. They released an offer to sell part of their refining capacity, and unfortunately, nobody bid on it. Nobody wanted to, even at a good price, nobody wanted to get that infrastructure. So in Rotterdam, at our colleagues at TU Delft, the university nearby, just a few tens of kilometers away, are experts in civil engineering and architecture. And what they're doing there is underground storage of hydrogen. And you know, if you've been to Holland, you understand that 1/3 of the country is below sea level currently. 1/3 is at sea level, and only 1/3 is actually above sea level. So they've been experts at underground storage of many things and pumping of water and so on. And so that's the underground storage. The other is if we have offshore wind, there's a natural opportunity to produce the hydrogen at those locations and potentially store that by underwater storage. So those are new technologies that we haven't been working on globally. In Houston, Texas, they have an underground storage of the depleted oil. Where they have, and so those are not the daily transients that most of us think about. That is, if we produce hydrogen and we need the hydrogen storage of because of the intermittence of renewable energy, then that becomes the things. We're countries, maybe like Turkey, where the natural gas lines, if we can increase the percentage of hydrogen without having a major capital investment, and do that safely, then the hydrogen pipelines themselves become a transportable as well as an energy storage, of the hydrogen. And it can help decarbonize on a small level the natural gas, which is already a relatively clean fuel compared to the other fossil fuels. So that is our immediate solution. In countries like the mining countries of Peru, where I've been working, they only discovered their natural gas about 20 years ago, and they only have 20 years left of that supply. The rest of it is in very well protected area in the Amazon that's preventing any future developments. And so that case, it's a transition of storage, and then also a transition. They know that natural gas supply will be depleted very quickly. If you do the more dramatic change of storage, the sort of longer storage, we can see back in Germany. They were dependent on the Soviet fuel, and they need to do a very quick transformation. And so the large storage underground in Netherlands provides them. Netherlands has the potential of having 100%, not of the residential, but of the transport lines. And so that's the integration. So the opportunities, if you look at that report from IEA, the large electrolyzer projects, the largest electrolyzer projects that are relevant to Europe is in Australia and producing the green ammonia. Now the challenge is the safety. And one is a conversion for engines or something, but the other part of the green ammonia is in terms of bunkering equivalent, and you need some type, instead of dikes of a liquid leak, now you need these water curtains. And one water curtain's not enough. We need at least two, and that means the land space is larger. Netherlands is not as compact as Singapore, but the port at Rotterdam is. And so much like Singapore, they're developing new artificially ran reclamation areas. In Turkey, then the challenge might be is if we develop offshore wind in certain regions, do we have something similar to that? And I would suggest that maybe we do that. I mean, we have fishing industries that have something similar, and yes, there's some challenges. But as we looked at that, the upstream, midstream, and downstream, the OPEC recognizes those challenges, but they also recognize that traditional oil and gas are the people that have those expertise in terms of the storage. The question is, which is the best fuel? And the maritime industry people in Singapore said, we know that ammonia is not the best fuel, but it has the total cost of ownership at the lowest for Singapore. And they know that they have to do that or they lose their position. So I think in this case, it's the economic driver is making the decisions, not necessarily efficiency. Does that make sense?
Thank you for the comprehensive answer, Professor. So
Yeah.
regarding Turkey, as you talked, we have started working on blending of hydrogen natural gas as a project. But the limit of 20%, 25% is a barrier to increase the amount of hydrogen in the gas pipeline. But we're still working on that project and trying
Yeah.
to hydrogen is
I saw a question here is what would be the best option in the chat for renewable hydrogen or nuclear hydrogen? So I think in Indiana, we're one of the recipients of the 7 hubs of $7 billion in funding, and ours was under a 3-state area where nuclear power is here. And at Purdue University, we have working with Duke Power for a small 25 megawatt modulating late generation nuclear power system, at least optional to consider that. The difference might be in nuclear power is in magnitude we're talking about 25 megawatt modular that could be institutional, an industry size, university size, but not in the gigawatt scale. So the nuclear doesn't scale up. In the US, right now, we get uranium from Russia. So it is strategic supply of uranium. So if we look at the demand for energy electrification, which is ongoing, and I have to say, I was lucky, a relative bid on the TOG, and I just bought last week a new electric vehicle manufactured, and so I'm happy to be a recipient of one of those electric vehicles made in Turkey. So what we need is in the electrification is renewable hydrogen at scale, and the scale at gigawatts. As an example, the country of Chile has an ambitious wind development program, 1.6 terawatts of wind power, 1.6 terawatts, 1,600 gigawatts of wind. Now, they are a supplier of the minerals that we need in the electrification. Copper. Copper in the next 7 years has a growth demand, 900% increase in copper. We just can't speed up production at a mine. So in that, we need that. And in the mining industry, typically, like at a copper mine we visit, you mine the copper, you extract it, but you also concentrate the ore in pit, and you use a lot of energy, a lot of water. But most of the minerals, concentrated, they're shipped as rocks around the world. What we need is to take the renewable energy that's built in excess, like in Chile, and then go ahead and smelt or make the copper refiner at the location. About 21 years ago, I was in Istanbul and went to a metal refinery, and think of what it was with large diesel backup power systems, because in a copper smelter, you can't have a power outage. And so you had to have these enormous diesel power systems. And they were so noisy that even in the building, humans couldn't go into it, even with air protection. So the renewable hydrogen for the minerals as a supply chain in the electrification for producing copper and other things. If we look at the copper concentration of use in renewable electricity in the cars, we get a significant increase just for the motors themselves, but also the voltage. Think of the electric car that we start out with somewhere around 400 volts. The buses were at 800 volts. Guess what the voltage is on the mining trucks? 2,600 volt, 5.6 megawatt power systems. So in those, a lot of copper. So that's a critical part. So we need that gigawatt scale. Nuclear doesn't do that. We simply, it does. We don't have the capability to scale up in a short period of time. It's the race to zero.
So thank you. We have another question. Of course, I would like to thank Dr. Mert from Canada that raised this question. This question is from the Yıldız Teknik University. Dr. Gencer is asking about the safety concerns of hydrogen during the production, the storage, and usage of hydrogen, and any advancement that we have maybe done in recent years about the security of hydrogen.
So let me give you the mining truck example. So we have 5.6 megawatt electric power system retard, and you have 2,600 volts, and you have hydrogen stored on the truck at 700 bars. So yes, it's a challenge. And so that the company that solve the problem, so to speak. It was a company out of Seattle, Washington. It's called First Mode. They had no experience in engines, no experience in fuel cells, no experience with hydrogen, but it's a design thinking company. And they developed it for Anglo American in collaboration with Komatsu, and in Chile with Caterpillar and one other company. And so in those cases, it was the design process. Instead of saying I have guidelines for safety, I have to go back and do a design thinking, sort of blue sky concept. And that company, First Mode, not only has responded with a 2-year full test at a gold mine in South Africa, they've actually have an order for 60 power units for mining trucks, and are now building their factory for the production. So I think it, as a grad student, it may be, instead of saying, do I go to work for a multinational company like a Caterpillar or something like that, or do I look for these really innovative, different process of designing for change? And design thinking might be, the common currency of doing that. And so I just, it turns out that in Singapore, I had an opportunity to take a short course, and it was a design thinking company out of Netherlands, and they did a demonstration of how you design for change. And part of it, as an example, to just give you a parallel, it was said, okay, instead of designing something technology, let's take a design that they were consultants with, and they did for the Olympics in 2024 in Paris. And so we say the opening ceremony, if we want to make the event successful, the opening ceremony when all the athletes march around in the stadium. But that has limitations, because unless you have a ticket to the stadium, you have to watch it on TV. And it's not the same as being there. You only get to watch it on TV. And so in Paris, the design thinking approach was skip the stadium and travel along the river. And after all, Paris is a city of lights. And so instead of having 100,000 people have tickets, they're going to have 600,000 people with seats along the river. And we have a parade through the river, and you see the whole city. And so if you think of that, how that change, which gives more, a magnitude increase. So in hydrogen safety, we have to do that design thinking. We have to think, it's not just thinking out of the box. We have to think, how do we make the impact at scale? So it's design for scale, not for laboratory safety, but, now we go to these large systems, and it really forces us to look at this sort of hub and spoke design as opposed to a uniformity across with the same sort of things. If you were in OPEC, they said, well, that's what we do. We don't have a refinery in every city. And we have strategic locations in refineries. Yes, in those locations, we might have higher emissions or higher safety, higher risk, and so on. So I think safety will be there. I see one question here on the chat in terms of hydrogen preferred use for biomass waste and plastic waste by pyrolysis. And that brings to the question of, say, solar thermal power. Of instead of material handling, can we do a pyrolysis approach or a high temperature solar thermal chemical cycles? And yes, those are there at scale, at cost. It doesn't, it begins to limit the locations. So, from a perspective at high altitude on an airplane, we need to look at something in scale. My flight from New York to Singapore is 19 hours, so it's a long flight, and at that we have to change the whole concept of service, if you will. So instead of serving food, before you take the trip, you order your meals. and you don't get served all at the same time. You get served when the meal is prepared. So as a child, your mother prepared food and you ate when your mother prepared the food. In that, we may have to look at the biomass waste and plastic waste. And I think in the United States, we have a program that I've been involved on where we say it's the nexus of water, energy, and food. And so the case study we did was in the mining district where the soil was so rich in minerals, any water became contaminated. Downstream, we grew the food and the water was contaminated, the minerals, independent of whether we had mining. So the mining projects have to instead of just divert the water, actually have to provide the clean water. So that nexus of water, energy, and food is there. Plastics, not all plastics are the same. So I think we know today that microplastics become embedded into the water that we can't necessarily filter out. So we have to, go upstream and reduce and eliminate those sources of those microplastics. The pyrolysis of burning isn't. So again, maybe from a student's perspective or grad student's perspective, is looking at it, that nexus of water, energy, and food. Those, the elements of sustainability for life. So we can't just look at the energy by itself or the plastics by themselves. We have to do all of that. So I think it's those mindset changes. So instead of just narrowing down with a very focus, we have to keep a broad perspective and integrate those systems. So to produce, is it preferable to use? I think we would have to look at maybe the needs base. What are the needs to do that?
Thank you very much. Any other question? I don't see any question in the chat box. So if still we have, let's say, 10 minutes or so for room for questions, if there's any. So it looks like, of course.
So let's make a comment about the automobile. So, some years ago, we did a project for General Motors, and we built, re-engineered a vehicle from a hydrogen fuel cell to a plug-in hybrid electric fuel cell vehicle. And so the fuel cell was the range extender. And so the new battery electric car from Turkey has 3 models: V1, V2, X10, X20. So the X20 is going to have twin motors, 4-wheel drive, and the 2-wheel drive, the rear-wheel drive, has 2 versions, V1 with a range of 300 kilometers and the V2 with 500 kilometers. So the supplier in Turkey then has said, okay, instead of investing in the hydrogen infrastructure and the hydrogen fuel cell, is we essentially have, versions to meet range anxiety. So if I was in Istanbul and I never drive the car outside, maybe the V1 model works. I have a house in Bodrum, so I need to go from Istanbul to Bodrum. So now I want the 500. The weather in Turkey is not so severe that I need the 4-wheel drive. So, for a needs base, the customer, the user, selects the right model without having to go to the range anxiety. Now, in the United States, I might need to drive coast to coast, and that's, depending on the route, could be 5,000 kilometers. And the infrastructure is not there for the fast charger, or we have a lot of people, and it's not, so in that case, we have a range extended, but it may be a plug-in hybrid electric vehicle. And so different markets are doing. Toyota have a new CEO. He says they've stopped the battery electric vehicle personal car development. They're backing out. So they'll stay and maybe go with a plug-in and hydrogen. So I think that it may be, from some point of view, it looks like we're moving forward and then we're moving backwards. And, the market drives, decisions from the corporations. Now, on the large industrial size, we don't have that option. We have to make the right decisions and we move forward. Now, clearly, what is happening is the stranded economic assets of fossil fuels. And those could be catastrophic for economies, like in Singapore, that is one city with, half the size of Istanbul. So it has to, it doesn't have an option to make the wrong decision. They have to eliminate their refineries. And the companies are doing that. So, Turkey may have a different challenge, and they have, pipelines and things that. So I think the strategy still has to be national, but we have to part of a global perspective and couple that. So, the question, say, for the automotive industry in Turkey may be that producing a battery electric vehicle that can export becomes an economic engine for the recovery of a country, and from that you develop, other tools. But in terms of safety, I think it's the challenge right now. If you were looking at research, we need sensors in low temperatures. Below -30, we don't have good sensor technology. So if we have facilities in very cold climates, high mountains or something, then those unique designs. So there's still sensor technologies. There's also sensor technologies that are, that have communication capabilities. So we can do real time. My wife Cheatham works as a software consultant for a company in Boulder, Colorado, that supports Salesforce. Salesforce now has a product that's called Net Zero Cloud. And in that case, they have an AI, they call it Einstein AI. And it's so you look at all three stages of emissions of carbon dioxide. So if you're in a business and you're looking at, here's hydrogen, I can mitigate my CO2, or I have a supply customer 2 streams upstream that has that opportunities. And so what you end up doing is wanting accountability. It's like having your currency, deposits of money in your check. So in the future, real-time data collection, big data in the cloud with sensors is a thing. So at Purdue University, we just opened up a new laboratory. It's big, $250 million building. In that, we're going to have a smart learning factory operational. So instead of having a classroom, a laboratory, we actually have a production facility. But instead of just the students learning to become smart, the factory itself is by itself through AI is going to be smart learning factory. So as we go through, a 2-year cycle on a product, the factory will have in its automation learn, become smarter. So if that's the future, then sort of the big data AI is a key component. Yes, there are ethical questions with AI, but I think, from a student's perspective, anything that we do in the future has to integrate the AI part, and that means sensors. So new sensor technologies with big data transfer rates instead of just analog to digital type of an approach. So sensor technology is clearly, and part of that is obviously in safety, but the other part is accountability.
Perfect.
I remembered one last comment. I worked for ASHRAE for a while, the American Society of Heating and Air Conditioning, and we had a conflict between flow meters, liquid flow meters. If we were from the API, the American Petroleum Institute, they were transferring commodities of high-priced liquids. If we were in air conditioning, it was closed cycle, so we didn't have. And ASME had a different market. And so the correlation coefficients, they were suing each other to find out what was the best correlation. We had three different needs, and we couldn't come up with an ISO standard for an orifice flow meter. So sometimes industry sectors have different demands, and the engineers can't come up with an ISO standard that we follow. The same thing goes in sensors. If we have a sensor that's unique for space applications, it's going to be quite different than residential natural gas lines in UK. So there are challenges, and sensors are obviously one of those. So again, I appreciate this opportunity to talk with you. Please share my email so that we do things. And if anybody is in the United States, in Indiana, please stop by and see us at Purdue University. Glad to see that.
Yeah, you also appreciate your time and your excellent talk. I don't see any extra question, and I would like to ask Professor Aysel or the student if you have any other comment, any last word, so we can conclude and terminate the session. If you have any other extra words to say.
I would like to thank Professor Sheffield for valuable outlook in hydrogen demand and hydrogen energy technologies. Our students are now can imagine or can plan what they are going to be focused on their PhD or other project or studies. Thank you very much again, Dr. Professor Sheffield.
Thank you.
Thank you very much for your very interesting presentation. Bye-bye.
Thank you, everyone. Thank you, Professor Sheffield, and have a nice day. Thanks.
Have a nice day. Thank you very much. Thank you. Bye.